You have probably already calculated the numbers. A portable air conditioner usually draws between 1,000 and 1,500 watts while operating. When the compressor starts, the surge can jump as high as 4,500 watts for a brief instant. Your inverter has to absorb that spike without shutting down. To keep one of these systems running off-grid for a full day, you would need around 8 400-watt solar panels, a large battery setup, and a pure sine wave inverter rated above 3,000 watts. Most off-grid systems are nowhere near that level. Even if you already own equipment capable of handling it, nearly your entire energy supply gets consumed by a single machine. What most people never mention is that another cooling method has existed across the American Southwest for more than a century. It operates on 12 volts. The build costs only $14. In dry weather conditions, it can lower the temperature of the airflow hitting your body by 15 to 25 degrees Fahrenheit. There is one major limitation, though. In places like Florida, Louisiana, or any region where humidity rises above 50%, the performance drops sharply. The system simply cannot work effectively in heavy moisture. You're about to learn exactly where this method performs well, where it fails, how it can be assembled in less than 1 hour, and how to maximize every degree of cooling possible. 2 common mistakes ruin the results. Those errors can reduce a 20-degree temperature drop to barely 5 degrees. Both problems are important. Now look at the actual power requirements. A standard 8,000 BTU portable air conditioner, which is the smallest size capable of cooling a room properly, normally consumes between 900 and 1,100 watts continuously. The instant the compressor activates, the motor surge climbs to between 3 and 4.5 times the normal operating load for roughly half a second. That means your inverter must support at least 3,000 watts of surge capacity. Most beginner off-grid inverters only handle between 1,500 and 2,000 watts. A portable air conditioner will overload them almost every cycle. The financial side is even worse. 8 400-watt solar panels alone cost between $800 and $1,200. Add a charge controller, wiring, batteries, and the inverter itself, and a dependable off-grid setup capable of powering portable air conditioning. Day and night ends up costing between $3,000 and $6,000 before the air conditioner is even purchased. That is not really an off-grid answer. It becomes a second expensive electrical grid. The harsh reality appears when battery storage enters the conversation. A 1,152 watt-hour portable power station, which falls into the mid-range category, can operate a 1,500 watt air conditioner for only around 30 minutes. On a 100-degree afternoon, the battery will be empty before the room temperature even begins to feel comfortable. The cooling process itself is simple thermodynamics. When water evaporates, it removes heat from the surrounding air. Each water molecule that changes into vapor carries energy away with it. The nearby air loses that energy and becomes cooler. The human body already relies on this same mechanism through sweating. A swamp cooler copies the exact process mechanically. Hot, dry air gets forced through a pad soaked with water. The water changes into vapor. Heat gets removed from the surrounding air and cooler airflow moves into the space around you. But there is a limit to this system, and it needs to be stated clearly. The method only functions when the surrounding air can still absorb additional moisture. If humidity stays below 30%, the temperature reduction can reach between 20 and 25 degrees Fahrenheit. When humidity rises between 30 and 50%, expect cooling closer to 10 to 15 degrees. Once conditions move above 50%, the effect becomes weak. Beyond 60% humidity, the cooler can actually make the room feel worse instead of better. The regions where this system performs reliably include Arizona, New Mexico, Colorado, Utah, Nevada, Idaho, Wyoming, Montana, California's inland valleys, plus the panhandle regions of Texas and Oklahoma. If you live in those areas, conditions are ideal. If not, another solution becomes necessary later on. This setup fits off grid living perfectly because evaporation itself needs almost no electrical power. Only airflow matters. A 12-volt fan typically consumes between 5 and 15 watts. A compact water pump that keeps the pad wet adds another 3 to 5 watts. Total consumption stays around 10 to 20 watts combined. One 50-watt solar panel can operate the entire system and still leave extra power available. The materials are simple. You need a 5-gallon plastic bucket with a lid. Those usually cost between $3 and $5 at hardware stores, or sometimes nothing if a restaurant gives one away. A 12-volt computer fan sized at either 80 or 120 millimeters costs around $3 to $6 through Amazon, or can be salvaged from an unused computer. An evaporative cooling pad or a thick cellulose sponge normally cost between $2 and $4 at a farm supply or hardware location. A compact submersible fountain pump ranges from $4 to $8. That pump keeps water circulating through the pad automatically, so constant manual attention is unnecessary. You also need short vinyl tubing to carry water from the pump to the pad. In many cases, the tubing already comes with the pump itself. Finally, a 12-volt power source is required. That can be a small solar panel, a vehicle battery, or a basic portable power station. The full project costs roughly $14. The first step is preparing the intake openings. Near the lower third of the bucket wall, drill or cut 3 to 4 openings approximately 2 inches wide. Space them evenly around the bucket. Those holes become the intake points where hot outside air enters, travels through the wet cooling material, and exits through the fan mounted on top. Placement matters. The intake openings must stay in the lower half of the bucket. Heat naturally rises upward. If the holes are positioned too high, airflow shortcuts through the cooling pad and fails to collect enough temperature reduction. Next comes installation of the cooling material. Cut the evaporative pad or sponge so it wraps tightly against the inner wall of the bucket while fully covering every intake opening. The material has to press firmly against all holes, so every section of incoming air passes through wet surfaces. This is where most people fail. Gaps are left between the pad and the bucket wall, allowing air to bypass the wet material completely. Waterproof tape can seal the edges if necessary. The third step is building the water circulation system. Pour between 1.5 and 2 gallons of water into the bucket. The water level should remain low enough that it never reaches the intake openings. Place the submersible pump at the bottom, then guide the vinyl tubing upward and across the upper edge of the cooling pad so water continuously drips downward through the material. This keeps the pad fully soaked without constant manual refilling. Under conditions of 90 degrees Fahrenheit and 30% humidity, the system uses about 1 gallon of water every 2 to 3 hours. The next stage is mounting the fan onto the lid. Cut an opening sized precisely for the fan so it fits tightly in place. Position the fan to draw air upward and out through the top. Pulling air through the wet material works slightly better than forcing air downward into it. Connect both the fan and pump to the 12-volt power source. Combined electrical draw ranges from 8 to 20 watts, depending on fan size. Now comes the second major mistake people make. Placement matters. Do not operate the system inside a sealed room. Evaporative cooling depends entirely on constant airflow. Warm, dry air must enter from outside, move through the cooler, and then humid air has to leave through another opening. If the room remains closed, moisture builds rapidly within about 1 hour and the cooling effect disappears. Open another window on the opposite side, approximately 2 inches. That cross-ventilation allows dry air to continue entering while humid air exits. Without this airflow exchange, the cooler starts fighting against itself. In real-world conditions below 35% humidity, the setup can reduce incoming air temperatures by 15 to 25 degrees Fahrenheit. In Nevada, at 20% humidity, builders have recorded room temperatures dropping from 95 degrees to 78 degrees. In Colorado, at 30% humidity, temperature reductions between 15 and 18 degrees remain consistent. At humidity levels around 45 to 50%, common in sections of the Texas Panhandle or Kansas during peak summer, expect cooling closer to 8 to 12 degrees. Still useful, though far less dramatic. For anyone living in the Southeast, the Gulf Coast, or the Midwest during humid summers, this approach is not the right answer. In those climates, a different off-grid cooling strategy works better. Radiant barriers, earth tubes, or a high-efficiency mini-split connected to a properly sized solar array are more effective options. There are also 3 upgrades that improve performance further. The first is doubling the cooling pads. More wet material means more evaporative surface area, which increases cooling potential. Just ensure the fan remains powerful enough to move air through the added resistance. The second upgrade involves adding ice directly into the water reservoir. Ice water lowers the wet bulb temperature inside the pad and can provide an additional 5 to 8 degrees of cooling while the ice remains frozen. 5 pounds of ice creates a noticeable difference during a 2-hour cooling period on a 100-degree day. The final upgrade is directing the airflow through ducting. Connect the fan outlet to a 4-inch flexible duct and route it directly toward your sleeping space. Instead of attempting to cool an entire room, the system concentrates cooling into a 3-foot area around your body. Simple physics, minimal energy use, and in the right climate, far more effective than most people expect. If you want more breakdowns on off-grid systems, survival engineering, and low-power cooling methods, stay tuned for the next report. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.